Hey guys, welcome back to another episode of the Real Hacker Hours podcast. Today I'm going to continue working on the Ghidra static bug finder. Particularly right now, what I'm wanting to do is revamp how I get the defining value for a varnode. What I mean by that is, let's say you have a varnode that is an input to an argument for a particular function. I want to know what that varnode value is. I'll look at like the defining p code and get the value from it. Right now, sort of how I do is I just iterate through the defining P code and just iterate through all the var nodes and just return the first one that isn't a constant. I'm wanting to implement logic where I actually will look at like what type of P code it is and then get the value accordingly, because that should give me better results in terms of actually trying to like trace through it. So let's get started. Okay, here's the function. Effectively, what I'm doing to start off with is I take an input var node, get the defining p code for it, check if it's equal to null, and then I will effectively iterate through and just run code based upon what type of p code we're dealing with. And let me pull this up. Here we have some docs that refer to like the different P codes and the corresponding like what the input and outputs for them are. You see here for copy, it only takes a single input, which is the source, and assigns it to the output. So for that, the var node that we're actually interested in tracing through is just going to be the one at input 0. For load, what is this constant ID of space to load from? Yeah, it's effectively just dereferencing the input and moving into the output. So I'm going to have it be the same as copy. What about store? Varnode containing pointer offset to destination pointer, or varnode containing data to be stored. In this instance here, there isn't an output. Like for copy, output is where the value is being stored. Same thing with load. Also, we're seeing there might be an actually, I did this wrong. Looking at load, input 0 is the constant to load from. Input 1 is the var node containing the offset to the data. So, like, input 0 would be the base offset, and input 1 would be like the offset from the pointer. So, let's say if it's like pointer plus 8, input 0 would be the pointer, input 1 would be the offset. Actually, for now, I'm going to leave it like that. Store 2. Input 2 is the actual data being stored. So I'm going to go ahead and have that be the value, the var node that is returned. For branch instruction doesn't at all deal with any type of data transfer, so you don't have to worry about it. Same thing with C branch. What about this? This is an indirect branching instruction. Address to branch is determined dynamically at runtime by examining the contents of the variable input 0. Okay, so this is just an indirect call. Cool. This is another call indirect return. What is this piece? Varnode containing most significant data to merge. This is a concatenation operator that understands the Indianness of the data. The size of input 0 and input 1 must add up to the size of the output, the data. Okay, so this is just concatenating input 0 and input 1. Now, in instances like this, realistically, the actual source of the var node is coming from two separate var nodes. However, this function here, the return type is just a single var node. So we have a choice here. we can either switch this to like a varnode list and just return like a list of them so that way we can deal with these, or we can just return a single varnode. For this, I think, hmm, for now, I'm just gonna have it return just a single varnode. In the event that I want that functionality later, I can just go back and change it, but yeah. So this is for a piece. Let's go ahead and do that. And I'm going to leave a comment here then. Okay. I'm wanting to return input 0 since that's the most significant data. Subpiece. This is a truncation operator that understands the index data. Okay, so this subpiece opcode is just truncating input 0 with input 1 being a constant, saying how many bytes to truncate. So for this one, I'm wanting the varnode I care about for tracing purposes would be the first one. What is this? Oh, this is a comparison, another comparison, a comparison, another comparison, a comparison, another comparison. Actually, do we care about compare? We would. Well, comparisons. They do set an output value, so we would care about them. Hmm. Yeah, we probably should implement that, but let's look at some of the other ones. Signed extend right here. Yeah, for that one, we just care about input 0, which we have that here. Int add, we care about input 0, 1, 0, 1. Carry. That's a nice P code operator. Negate. Just gonna quickly look through these real quick. Okay, Okay, after thinking about it a little bit, I want to change this to a varnode list. That way, what I can effectively do for like these opcodes like add, divide, compare, that frankly can derive their value based upon multiple different input varnodes, I can effectively trace through that. So what is this going to mean? We're going to need a let's try to make this work. Varnode list. And we will need to, I'm going to just comment out these lines real quick. That way we can just verify that the code I did right does indeed work. Oh, forgot to. Yeah, this is going to crash. Yep, it crashed. Oh, equals new. Okay, let's go ahead and do this. Actually, I am doing this wrong. This is a Varnode. Okay, need to convert Java list to array. I'm gonna pause. This is just a simple Java thing. I'm just gonna pause the video while I just Google how to do that real quick. Actually, scratch that. We could just change this to a varnode list, because practically speaking, it really doesn't make too much of a difference between that and an array for our purposes. So now we could just convert all of this over. Dot add. Dot add is the yep. Just gonna copy this. Okay, cool. Let's make sure that this runs. Okay, that runs just fine. Cool. Now let's go through this list and make sure that we didn't. Well, that we got. Now that we're looking at all of the input nodes that we care about. Let's make sure that we have them. For copy, it's the first one. For load, it's the first and the second. I'm going to just go ahead and add a comment here just to say like what the value that we're storing is. From pointer offset to data. This is the base pointer. Offset from pointer. Okay, cool. Now store. For this one, we only care about. Oh yeah, we only care about the second one. Reason for that being, with this function, we're interested in like what is the source of a var node from, and for store, first and second var nodes signify the destination location, but only the last one, the third one, specifies the actual value being stored. Branch, don't really care about. C branch, this is just a conditional branch, doesn't actually set anything. Indirect branch, it's call, indirect call, return, piece. Oh yeah, we do care about this one since it has both it concatenates two things that are, the first one's the more significant, has the more significant bytes, the second one has the least significant bytes. So, more significant bytes to merge. And this next one has the lesser. Okay, for sub piece, Yeah, we only care about the first argument here because that's the only one with data. That data is being truncated. The second one is just a constant signifying how much data we want to be truncated, so don't really care too much about that one. Next up, we have the comparisons, which for those, yeah, we care about both of the varnodes. However, the thing is with these is we want to check if either of them is a constant. Because, yeah, we're right now interested in where this value stems from. And if it's stemming from a comparison, well, do we want it to be a constant? I'm just going to save it both for now and then worry about that after I am returning the values. So let's go ahead and do this. We have one, let's start with an equal and an not equal. We're going to saving input 0 and input 1. And this is going to be for equal, not equal, less, and s less. And then we have less equal and s less equal. Okay, I'm just going to make sure that the code that I wrote so far actually works, but via running the script. Okay, it works. Cool. Let's continue. We have Zext and signed extend, which I believe I already have those. Yeah, they're right here. Zext and signed extend. And next we have the mathematical and logical operators. Just gonna, what is this one? Oh, modulus. Negate and equal. Oh, and then we have the float operators. That's gonna be fun. Okay, cool. So let's get back at it. Where did we leave off? We left off with, oh, sorry for breathing. Yeah. We left off on add. Okay, cool. For this one, it's going to be similar to this one. This is going to be int add. Yeah, for add, it just takes two inputs and adds them together, and that's what the output is, so we care about both of the inputs. And it's going to be the same thing for sub, carry, for unsigned addition, overflow, or carry conditions. Yeah, what is this? Okay, these two look like they just check for integer overflows. This one for unsigned, this one for signed, so we care about that for both of them. Yeah, same for that one. This one, we only have one. Oh yeah, it just negates a single input, so we only care about the first one, but I'm going to do it, write the code for add through sborrow. So that's going to be one for sub, one for carry, one for scarry, and one for sborrow. Let me think. I just thought of a way better way to do this, at least from the perspective of this. So what we have here is we're having most of these, frankly, are like the same thing. We're either grabbing the first var node or the first and the second var node. So what we could do that's way better than this is just have like a hash map of the values and just simply get it. If the key is equal to 0, we only get the first argument. If the key is equal to 1, we get the first and the second. Or if the key is equal to, excuse me, third, we get the only the third argument or something like that. So let's go ahead and do that. Hash map integer. Why integer? Because the enums that we use to signify the opcodes are integers. Argument mapping equals new hash map integer. Let's make sure that runs just fine. Okay, cool. So that works just fine. Let's go ahead and start putting some of them together. Integer mapping dot put. And we'll put 0 for that, signifying only the first. Second. Just going to go ahead and remove this code and just paste it over another terminal so I can just effectively move that over here when I need to. It's going to be for store int args to retrieve equals argument mapping dot get or default def pcode dot get opcode or -1 if args to retrieve is equal to 0, then do that, else if args to retrieve is equal to 1, else if args to retrieve is equal to 2, else, okay, cool. And this will be the catch-all, okay, cool. So let's go ahead and do this. We missed a few things here. We got rid of the Varnode list. We need to remake that. Turn Varnode list. Oh wait, no, it's right here. Let's just go ahead and move this stuff up since I accidentally moved it below. So if that equals that, then we can just, for only a single argument, we do that. For the first and the second argument, we do this. And for just the third argument, we do this one. Okay, let's go through and just add all of these. piece, subpiece. For piece, we want the first and the second one. For subpiece, we just want the first one. For Zext, we just want the first one. Same thing for signed extend. For int equal, we want the first and the second. Same with all of the other comparisons, which I'll do right now. Same with signed least, or signed less. Next we have less equal, yeah. And next up we have the logical operator, or the math operators. So that one. Asparo. And that's where we left off. Okay, next we have integer 2 comp, which just negates the input, so that's going to be number 1, since we only want the first argument. Just go ahead and make sure that this still runs, that we didn't introduce a typo somewhere in the code. And that we did. We defined def p code after we first used it. Let's see, apparently, is it not? Oh, it's not equal, not non-equal. Okay, cool, let's fix that. Okay, so that runs just fine. Let's get back to it. We are at int 2 comp, next is int negate. Takes the, we care about the first and the second argument there, so let's reflect that in the code. XOR is the first and the second one. Same thing with AND. Same thing with OR, left and right. Signed right, yeah. Multiply and divide, same thing there. Oh wait, this should be a 1, not a 2. Okay, that's right. Right. Next we have signed right. Multiply and divide, let's add that. and divide, remainder, and these three next. Remainder. Boolean negate, we only care about the first argument. So that's going to be 0. Should probably replace the 0, 1, and 2 with actual enum names. Boolean XOR takes in 2 values, so we care about both of them. And then we have bool and bool or. Bool and bool or. Okay, cool. And then next we have the floating operators. Which after that, I'm curious, what do you have after them? Okay, so all of the rest of these are just floating point operators. Let's see, we have float equal, which that's a comparison between two floats, care about both of those inputs. Float non-equal, same thing. Less equal. So these are all comparisons. We care about the first two. Add, subtract. Care about the first two. Multiply, divide. Care about the first two. Negate. We care about. Well, there's only one input, so we can only care about it. So let's go ahead and do these ones. There's 1, 2, 3, 4, 5, 6, 7, 8. So let's go ahead and make 8 of these. 1, 2, 3, 4, 5, 6, 7, 8. Float equal. Float not equal. Float less and float less equal. Float add, float sub, and float mult. Float multiply, okay. And then preceding that we have float divide. And then looking here, next one we have float negate, which you only care about the first argument. Same thing with a float absolute value and float square root. Float ceiling, this operation rounds inputs. Okay, it rounds it. Floor, round. Checks if it's not a number. Converts over to integer. Floating point precision calculator, I think it calculates what degree of precision the floating point is. So we have a bunch of, the rest of these just take in a single argument. So just look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can just copy this. 2, 3, 4, 5, 6, 7, 8, 9, 10. Starting with negate. Then absolute. Then square root. Then CEIL, ceiling. Next up, floor. Then round, then not a number. and then integer to float, float to float, then float to float, and then finally truncate. And okay, cool. So that's all of the Ghidra P code. So we now have a function in place that will, we can give it a varnode. It will look at the defining P code and give us the input arguments that we care about. Yeah, I'm going to end off the video here. Thank you for watching.